right, welcome back, you guys. We're going to take a look again at the slope of the tangent. So we'll find the slope of the tangent, which is the derivative of the point. If we have the point x, we go out x plus h amount, and we have this curved line here from x, f of x, to x plus h, comma, f of x plus h. And we said if I want that slope of the tangent right there, I'm going to have to use the slope of the secant, but the limiting process on that, right? So we went the limit as h goes to 0 of y2 minus y1 over x2 minus x1, right? And that was what our derivative was. Slope of the tangent line, which is the derivative at x, right? So let's go ahead and do it again here. We'll do it for 1 minus x squared. So let's find f prime of x. And then we're going to find the slope of the tangent at a few different points, since we have this derivative function. So limit h goes to 0, f of x plus h. So in this case, it's 1 minus x plus h squared minus the original function, 1 minus x squared, all over h. Minus 1 plus x squared. Go ahead and distribute that minus through. And notice minus x squared plus x squared, that's gone. I've got a 1 minus 1, that's gone. Remember, I can't plug that 0 in. I'm indeterminate, it'll be undefined. So I got to factor out an h from that negative 2x h on the top, and the h squared minus h squared. So I take an h out of each of those terms I'm left with. So then notice those h's cancel, right? And so we're left with negative 2x minus 0. In other words, the derivative is negative 2x. So the slope of the tangent at any x value I can find now. Remember, this is the function 1 minus x squared. Let me draw that. Here's 1 minus x squared, right? Looks kind of like that. And they want the derivative first at negative 3, f prime of negative 3. Well, at negative 3, it goes down here, f prime at negative 3 would be f prime at negative 3. The slope there would be 6. So the slope of that black line I tried to draw is a positive 6. Slope of the tangent at negative 3 is 6, right? That's what that's saying. F prime of negative 3 is negative 6. So again, this f prime of x is very useful. I can find the slope of the tangent at any point. The next one they want is at 0. Well, f prime at 0, you could probably see that. Slope of the tangent at 0 is 0, right? F prime at 0 is 0. So slope of the tangent at 0 is 0. Now let's do one more. They asked for f prime at 1/2. F prime of x is negative 2x. Let's find it at 1/2. Negative 2 times 1/2. I got negative 2 over 2 is negative 1. So right here, that slope in green, I didn't draw that very well again, but get the idea that that slope there is negative 1. F prime of 1/2, negative 1. Before we take a look at this second here, which is asking us find the derivative of y equals negative 5. Remember, y equals negative 5 is that horizontal line, right? So when you do this, you should end up with a slope of 0. Yeah, at any point there, your slope is definitely going to be 0. But we'll go through the formality of it so you can see it here. Limit as h goes to 0, f of x plus h minus f of x, h. Well, the function is negative 5. There's no x to plug into, minus the original function, negative 5. This is all over h. So I get negative 5 plus 5 is 0 over h. Well, 0 over anything is 0. So f prime of x is 0. So it doesn't matter what you plug in. If you plug in negative 100 as an s, you're still going to see that that slope is 0. Let's keep going. This next one here. How about the square root of x plus 6? Here's the square root of x plus 6. You can find it by finding the derivative. You can find the slope at any point that we wanted to. F prime of x equals limit h goes to 0, f of x plus h, f of x, all over x plus h minus x. Again, x is canceled. So we got limit h goes to 0, f of x plus h. So square root of x plus h minus the original function all over h. Notice the x's cancel. Now we're going to have to multiply by the conjugate is the way to deal with these radicals. Square root of x plus h plus the square root of x. If I do it to the top, I got to do it to the bottom. So I got square root of x plus h, square root of x plus h. That's just an x plus h. Now the outer and the inner are going to cancel each other, so I'm not going to even bother to write those. But the last one's negative root x times a positive root x is just a minus x. And now notice these x's cancel. And so I'm left with h over h square root of x plus h plus root x. And my h's cancel. So I got limit h goes to 0 of 1 over square root of x plus h plus root x. Now let's throw that 0 in. So we got 1 over root x plus 0 plus a root x. Well, root x plus root x is 2 of those root x's. So f prime at x is 2 root x. So let's say we plugged it in and we want to find the derivative at an x value of 1. That'd be a half. Let's go up here and look at that. So right here, when x is 1, this slope is a half, up 1 right 2, right? All right, here's our next one. Let's go ahead and find the derivative. Limit as h goes to 0, f of x plus h minus f of x all over h. So this will become limit as h goes to 0 of 4 over square root of x plus h minus the original function of 4 over root x. This is all over h. I do need to get this to have a common denominator, so I'm going to give this one a square root of x. I'm going to give this one a square root of x plus h. And so what we have is the derivative being the limit as h goes to 0 of 4 root x minus 4 root x plus h all over this common denominator. And this is all over h. Well, this is h over 1. So I'm just going to go ahead and multiply by 1 over h, top and bottom. Now I have one big fraction here, so I got f prime of x equals limit h goes to 0, 4 root x minus 4 root x plus h all over h square root of x square root of x plus h. And now we're gonna we look at that, and I'm like, well, I can't plug h in. I can't let h be 0 because now I'm going to be dividing by 0, right? So I've got to manipulate this again and multiply by the conjugate. 16x, and then, so there's that one. The outer and the inner will cancel, and you'll be left with minus 16 squared x plus h, and squared x plus h is just an x plus h. Well, 16x minus 16x minus 16h just leaves us with our minus 16h. And that is what we wanted right there. Got to have that h cancel. And now if you look at it, you're like, oh, this is nice. I got negative 16 over square root of x, square root of x plus 0, 4 square root of x plus 4 square root of x plus 0. Oops. Square root of x times square root of x, just x. 4 root x plus 4 root x is 8 root x. So I have negative 16 over 8. Let me write it this way. Negative 16 over 8 x root x, which is negative 2 over x root x. Or if you want, you can write it as negative 2 over x to the 3 halves, right? X to the 1 times x to the 1 half is x to the 3 halves. Or negative 2x to the negative 3 halves, right? There's another way to write that. Do a couple more here, you guys, and then we'll get into some conceptual discussions about the derivative here. I'm going to give this one an x squared. And give this one an x plus h squared. And then this is h over 1, so I'm going to multiply the whole thing by 1 over h, the whole thing. 1 over h, top to bottom. Okay? And so we've got this limit as h goes to 0 of 1 over h times, I've got x squared minus x plus h squared. This is all over that common denominator, x squared, x plus h squared. Distribute that, and notice that the x squareds cancel. So you have x squared minus x squared gone, minus 2xh minus h squared all over. And I'm going to go ahead and that is x squared, x plus h squared. Let me take that h through bottom there. So I've got, and I'm going to take an h out of each of these terms on the top. Negative 2x minus h. Bottom has an h, and then the x squared, then the x plus h squared. We want that to happen there. And now we can plug the h in being 0, and we'll have no problems. And so we got negative 2x over x squared times x squared, x to the 4th. So we got negative 2 over x to the 3rd. I have a little bit different notation, you guys. There's a bunch of different notations. Remember, Newton and Leibniz both developed the calculus, and we use mostly Leibniz's notations, but Newton also obviously has some influence on that as well. They developed calculus at two different areas at the similar time frame, so they're both credited. But anyways, dy dx at x equals 3, that's the same thing as saying find the derivative at 3. Okay, that's saying the same thing. So dy dx, same thing as f prime at x. Okay, those are the same thing. And you can also write it this way, the derivative of y. So all three of those are saying the same thing, dy dx. So what we have here is we have y being x cubed plus 2. And I'll use a little notation on this. And I'm going to run the derivative on this. I'm going to run the derivative with respect to x here. So I have dy dx. This is f prime of x. F prime of x is the same thing. Is. So I'm running the derivative. Well, the derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. So we've got to run this. When as h goes to 0, x plus h cubed plus 2 minus the original function, x cubed plus 2 all over h. So dy dx, the derivative, f prime of x, same thing, x plus h, x plus h, x plus h. Let me do the first two here. I got x squared plus 2xh plus h squared. Notice the 2 minus 2 is gone. Now let me take the x through to each of those, and then I'll take the h through to each of those. So I have x cubed plus 2x squared h plus xh squared. Then I'm going to take the h through plus x squared h plus 2xh squared plus h cubed. I still have this minus x cubed on the end. And then notice I do have some like terms. That one and that one are like terms. So 3x squared h. Should have done that in green, huh? And then xh squared and plus 2xh squared. So I got 3xh squareds. And then I have the h cubed and a minus x cubed. And notice the x cubes are gone. And so I can factor out an h. I have 3x squared plus 3xh plus h squared over h. So I can cancel that. Remember, I'm taking the limit as h goes to 0 on this. So I have 3x squared plus 3x times 0 plus 0 squared. Well, that ends up being 3x squared, right? Because those are gone there. So the derivative, f prime of x, or dy dx, is 3x squared. Now, they wanted this. They gave us this notation. Find it at x being 3. So 3 times, so throw it in. 3 times 9, 27. That's the derivative when x is 3. Y dx, x equaling 3. So just a little different notation you should play with a little bit. Okay. I also think, actually, I think it asked me, I forgot this part. Then use it to find the equation of the tangent line at this value. Well, at this value, 3, x being 3, all right, we have this function, f of x equals x cubed plus 2, which looks kind of like this, right? So if I plug 3 in, what point is that? I got 29. 3. So f of 3 is 27 plus 2. Whoops, 29. So 3 comma 29. And we already know the slope was 27. So now I just go y minus y1 equals m x minus x1. Right? And then that'll whittle that down. That'll be 81. There's the equation. If I had it way up here, that's the equation of that red line at 3, 29. Sorry, I did that a little too fast. Negative 81 plus 29. Thanks for pulling that out. That's a minus 52. Sorry about that. All right, this last part we're going to talk about when do you have a derivative. And what I want you to remember is that differentiability implies continuity. So if you're differentiable, then you're continuous, not necessarily vice versa, okay? In other words, even though you may be continuous, you may not be differentiable always, okay? But differentiability does imply continuity. Let me give you an example for a minute. If you think about the absolute value function, oops. All right, here's our absolute value function. And if you were to run the derivative from the right-hand side, right? So you're finding the derivative from the right-hand side. So limit as h approaches 0 from the right, and you were to go through this, right? And so you're using just x for the absolute value of x, because y equals x whenever x is greater than or equal to 0 for the absolute value function. And you would end up with, well, what's this slope? 1, right? You'd end up with a slope of 1. If you did it on the left-hand side, what would your slope be? It'd be negative 1, that's right. So your derivative would be limit, h goes to 0 from the left, though, and you did all this, and it's negative 1. Well, they don't agree. The limit from the right-hand side does not agree with the limit from the left-hand side. So you don't have a limit there. You don't have a derivative. So a sharp point is a problem. You can't take the derivative right there on the absolute value. So no sharp points for derivatives. So this is a problem, right? It's a sharp point here, right? So let's answer the first question. And of course, any breaks in continuity will be an issue. And if you remember, to be continuous, there had to be no holes, jumps, or gaps, right? Remember that? It has to be nice and smooth. Can't lift up your pencil if you're drawing it, right? So the problem with B is there's a hole there, right? And at point A, you know what? Let's do a little bit more notation here. At point A, there's a cusp, so no corners. So what's happening is the left hand and right hand limits do not agree when you're finding the derivative limits, right? Think of the absolute value discussion. At point B, this is a problem because there's a hole, right? And you must be continuous. I know there's a limit there. There is a limit there, but it's got to be continuous there. It has to be defined. It must be continuous to be differentiable. Must be continuous to be differentiable. Well, the problem with this one is we've got that big gap there, right? At D, I'm jumping to D, sorry. So we've got the big gap. Limits do not exist here because of the gap, right? So there's no derivative there at D equal either, okay? Now lastly, what about C? Why is C a problem? Let me try and put C on here. So there's the point at C. Well, it looks like it's filled in, it's continuous. What's the problem? Well, this slope is, if you were to draw this, the slope is perfectly vertical. Well, what's the slope of a vertical line? It's undefined. Yeah, so the slope, that's the whole problem. The slope of the tangent is undefined. So remember, that's what a derivative is. It's the slope of the tangent. Well, the slope of the tangent is undefined, so there's no derivative there. The tangent's vertical. Okay, so those are all issues for that. All right. All right, let's go ahead and take a look at this one here. Let's actually kind of draw this thing. We've got the piecewise defined function y equals 2. So here's y equals 2 normally, right? Our horizontal line. But it's only when x is less than or equal to 1. Only that part of it. When I'm less than or equal to 1. So let me erase the right hand of that. Only when I'm less than or equal to 1. So there's that part of it. And then we got y equals 2x. Let me do that. Y equals 2x when my x is greater than 1. So I have a hole right here. I'm not including 1, but I can pick values more than that. And I could plug them in one by one. 2 times 2 is 4, 3 times 3 is 6, and so on. So 1 comma 2 is open, but 2 comma 4, 3 comma 6, and so on. Now, normally I would open up 1, 2, but it's already filled in right there at the point. So notice this is a continuous function here, right? And then it says find f prime at 1 if possible. Well, what do you notice from the graph? What do we have right there? Is it smooth and continuous? No, again, that's what you want to remember. It's got to be smooth and it's got to be continuous to be differentiable. It's not there. I've got this little corner. So the left hand and right hand limits are not going to agree there, and so it's not differentiable. Just from the graph, I can see that this is not differentiable. Not differentiable at x being 1. All right. Now, if you were to run through the limit, you'd say, well, if you do it for the f of x equals 2, and you were to run through the limit as h approaches 0 from the left, f of x plus h minus f of x all over h, and you'd get this to be 0, and then you'd do it for 2x, and you'd run h 0 from the right, and you'd run through this, and you'd get 2, and you're like, well, if this on the left, this slope is 0, but on the right, the slope is 2, those don't agree, right? At x being 1, right? All right, let's take a look here. First of all, part A, at what domain points does the graph appear to be differentiable? Well, where is it not differentiable? Let's answer that. Where is this thing not differentiable? Where is it not smooth and continuous? And hopefully you say, well, negative 1's a problem. 0's a problem because I got this gap right there. And exactly 2 because we got the hole, right? 2. So other than that, it's differentiable. It's fine, other than those areas. So we're trying to say, where is it differentiable? Well, the domain goes from negative 2 to 3. So I'm going to start at negative 2 up till negative 1. Negative 1's a problem. So I stop at negative 1, and then I go up to the next problem, which is 0. I stop at 0, and then I go up to the next problem, which is 2. I stop at 2, but then I got to finish out up into the very last part of my domain there. So I just have those breaks there. All right, that would be my answer for where this thing is differentiable. Part, where is it continuous? Where is it continuous, but it's not differentiable? It's filled in there. I can draw it through this area, but I cannot have a corner like that or a cusp, right? Remember, it's got to be smooth and continuous. So that's where it is. It is continuous, but it's still not differentiable there. Remember, differentiability, if you're differentiable, you're guaranteed to be continuous. But it's not necessarily the case the other way, and that's the example with that one that I'm pointing out. It's continuous through there, but it is not differentiable because the limits from both sides do not agree. right? All right, where is this thing neither continuous nor differentiable? Right? That would be an issue. Not continuous through there. I can't draw it without lifting my pencil. Can't draw that without lifting my pencil. So 0 and 2, not continuous nor differentiable. Okay. Well, I hope that helps, and thanks for watching, taking notes. See you guys next time.